Welcome back. So I decided to jump back 4 slides. So whoever's new who hasn't been following my talk, the first part this morning, I was talking about digital signals. And a digital signal is simply a signal that is both discrete in time and in value. So it only exists for discrete time steps, and it may only exist for discrete values. So what we're seeing here is samples of a signal that we digitized. And it's not hard to see that this was the original signal, a sine or cosine signal, and we sampled that at a fixed frequency. In this case, in one time step, we had 3 values, so we had a sampling frequency of 3, and it's pretty obvious that the intuitive approach to reconstructing the original signal from this is to connect all these lines with a smooth line, come up with the original cosine, and be happy about that. However, we figured out that that's not the only way to explain the same samples, right? We can see that this cosine, which is totally not the same cosine as this one, explains the same samples. So there's ambiguity. We don't know whether the observation we got was from a cosine with a frequency of 1 or from a cosine with a frequency of 7 or 13 for that matter, or actually any multiple of the sampling frequency above the observed frequency. So we were at a point where we could deduct that digital signals have a periodic spectrum, and the periodicity of that spectrum is f sample actually. So the sampling rate. Hence, the postulations we have to make are, if we don't know whether a signal that we observe could be caused by a cosine of frequency f, or a cosine of frequency f plus n times the sampling frequency, we must first restrict the amount of cosines we might actually see, right? So this is the postulation we have to make. Before sampling a signal, we must make sure that it's sufficiently band limited. So every single receiver, digital receiver, will have some filter ensuring that this makes sense. Otherwise, all the things at multiples of the sampling frequency will alias down into a place where we can't tell them apart. So, as I mentioned, this mechanism of things from higher frequency or other frequencies appearing at where we think they are is called aliasing. It's usually something that we don't want because, well, we don't know what happens then. And of course, that's not only cosines, that's also noise will alias into our band. So we don't want that, so we have to keep up the noise, so we filter. So the typical anti-aliasing filter is a low-pass filter because, okay, if we're after this cosine and don't want to have this cosine, then we just exclude every cosine that is faster than that, right? Or at least we cut off below that one. So, but there's another trick we can do. We can actually, and that was where I left off this morning, we could actually apply this aliasing mechanism to get higher parts of the spectrum down to where we're observed by simply sampling lower than they are. So we can shift them by n times the sampling frequency. Again, we still have to limit the bandwidth that we observe, but it doesn't have to be the lowest bandwidth. It can also be a higher, we call this Nyquist. So for all practical reasons, this is great, right? We can do receivers without having mixers that way. It gets a little complicated in practice because having a filter that filters out everything from 0 to what's, let's say, 5 gigahertz to observe something above 5 gigahertz, and then have another filter that filters everything out that is above that 5 point something gigahertz. That's going to be expensive, and it's probably not going to work because no perfect filters are in existence. So, sorry, I have to talk into the phone. So, the typical very frequency agile device still works by mixing things down from high frequencies. Again, for low frequencies relative to the sampling rate, let's say 2, 3, 4 sample rates above the first Nyquist. This works. It gets harder above that. So let's go back and look at spectra of digital signals. So we have a cosine here. That cosine is this wave, and we can't actually tell whether it's a cosine of pi x or a cosine of minus pi x because, well, it's symmetric to the 0, and we can't tell that. So the cosine actually has a spectrum that has both the minus 1/2 and plus 1/2 frequency in there. And because we want to have total power of 1, their amplitude is 1/2. So that's nice. That's physically sound. Now, because, as I said, there's ambiguity in here, the same spectrum repeats every f sample. So, as I mentioned before, we sampled with a sampling rate of 3. So we have the original 1/2 and minus 1/2 tones, and we have the 3 minus 1/2 plus 1/2 tone, and the minus 3, and so on. And this continues forever on both ends. So this kind of falls from the skies right now, and I really don't have the time to go into complex signals right now, but trust me, real signals as observed by a single ADC observing a single voltage have symmetric spectra in the sense that they are Hermitian symmetric. So the real part is symmetric to 0, so the value of the spectrum at plus f is the same as the value of the spectrum at minus f for the real value, and it's the other way around for the imaginary part. Since what we usually consider the power spectral density, or can observe and measure and estimate, is a real valued magnitude thing, we don't actually care about the sign of the imaginary part here, and just stick with the magnitude and can't observe the phase. So for all reasons, when observing a spectrum, real spectra are symmetric. So that means that the positive half of the spectrum at any rate fully defines the negative half of the spectrum, right? And we're repeating the same spectrum at f sample. So efficiently, or in effect, we only have 1/2 of the sampling rate as freedom. We can't define the whole sampling rate, which is in bandwidth with the real signal, because, well, half of it must be the mirrored version of the other half. So that leaves us with a very, very interesting point. If we want to sample a signal consisting of a mix of harmonic signals, then we have to make sure that the bandwidth is half of the sampling rate. Otherwise, bad things will happen. And to explain the bad things that would happen, I have this graph here. Well, this is the case where we didn't take enough care to actually limit the bandwidth. So this is f sample half, right? And the other dashed line is minus f sample half. So the total bandwidth between the two is f sample. And the moment we do this, and we know that our spectrum repeats with f sample, we'll notice that, now we have the negative part of the spectrum lapping into the positive end. So the orange thing, the real and the curve that I marked orange, is actually signal that adds up in places we don't want it. So this is aliasing in its worst form. We actually get distortion at the band edges, and this might, if we actually care for things that happen in the orange area, this is going to be bad. So we first have to filter to make sure f sample half is the highest frequency, or actually lower than that, to make sure that we take care of the so-called Shannon-Nyquist sampling theorem, which is really the very, very foundation of digital signal processing. Whoever tells you his receiver can do more bandwidth than half his sampling rate is either lying or not having a real sampler. There's ways to do complex sampling for complex signals, but in general, when observing a real signal, you cannot do more than f-sample half bandwidth at once. So there's plenty of examples where we have to apply that knowledge in the real world. For example, the classical sound card, right, has sampling rates of 44.1 kilohertz, 48 kilohertz, 96 kilohertz. Some studio equipment has a totally over the kill 192 kilohertz sampling rate, and the point is that human perception kind of cuts off after 16 kilohertz. There's rumors, let's say, that perception of specific music increases if you have like 20 kilohertz, but that's all. You don't need to get higher. So with 44.1 kilohertz, you're on the safe side, actually, because that's plenty more than twice 16 kilohertz. The nice thing about the Shannon-Nyquist theorem is that it not only says it's necessary to sample twice as fast or actually faster than twice the highest frequency, but it's also sufficient. That means that for every signal that does not contain frequencies higher than f max, I don't need anything more than twice f max as sampling rate, which is great because whoever is going to try to say an ADC with 100 kilo samples just so you can observe your local weather station, it's not going to be worth anything unless you can apply noise reduction that way. So, however, well, we are in a world where we can actually freely choose how much bandwidth we actually want to use. So in a system where we actually just want to communicate over voice, we can do with much lower bandwidth. Simply because, well, to understand me, you don't need the full 16 kilohertz bandwidth. 5 kilohertz should totally suffice if communication is clear. Actually, there's a lot of DSP that goes with a high sampling rate and then reduces the sampling rate by filtering in the digital domain and just transmitting what is necessary to understand, not necessary to get the full impression of a classical concert. Yet another example. We were talking about super heterodyne receivers this morning, and this is a kind of typical superhet receiver, right? We have an intermediate frequency at 70 megahertz, and we mix some ISM band signal down there and use our nice, cheap, and very steep analog SAW filter to filter out everything outside minus half a megahertz and plus half a megahertz of that center frequency, 70 megahertz. So this is nice. We get 1 megasample bandwidth. Problem being that's at 70.5 megahertz. So if we didn't know about the undersampling aspect, we'd assume that we need to do sampling with at least 141 megahertz, which is totally practical, but kind of expensive. And also totally overkill, because our effective bandwidth is actually just that original 1 megahertz. So 2 megahertz of sampling rate is totally sufficient. You typically want to mix down after having your IF filtered again, so that you don't have this high f-sample multiple filter problem that I mentioned when I introduced undersampling. But this is a total valid system design. So let's now look at a little more of a practical system, very minimal practical receiver, in fact. So what I'm showing here is a screenshot of a GNU Radio companion flow graph. So few of you might not know GNU Radio. So GNU Radio is actually just an SDR and DSP framework where you wire up signal processing blocks which start to exchange samples, do their DSP internally, and achieve the overall functionality. So in this case, the whole system looks like this. We have a user P source. Okay, user P is a software-defined radio front end. This is our sampler, our analog to digital converter that gives us a 25 megahertz samples per second in complex signal. So then we figure out why do I do this? Why do I do this? Well, I figured maybe I want to build a FM broadcast receiver that's actually able to receive all the broadcast radio channels in the FM band in Germany at once and write them to disk. So at one point, I want to cover the whole 87 megahertz to 108 megahertz bandwidth with my receiver, and then channelize that in the digital domain, decode that in the demodulate that in the digital domain to audio streams, and just write the audio to a disk, right? So this is just a prototype for the first channel. I decide that, okay, my center frequency between 87 and 108 is 97. I want to get the channel at 107 megahertz because that's my favorite station. So I use a frequency translating FIR filter first, which shifts the frequency, the signal in the frequency domain, filters it, decimates it. Then I do the FM demodulation. Then I do a resampling, which is necessary to match the audio, the sound card sampling rate, and then I just output the audio. So after having had a look at what this should do in practice, let's actually look what the individual components do. So at first we have the user P source, which is again a software block. It just says, okay, instantiate this module that will get samples from the user P. And tells the user P to tune to 97 megahertz to give us 25 megahertz of bandwidth, sampling rate, which in this complex sampling case is actually the same as the maximum bandwidth, and then just start streaming samples through that flow program. So we should probably talk about the user P here that's doing the actual signal processing, because like this really sounds like, okay, we have this analog device, and at the end it's an ADC, and then we just push in the data through the PC. And as mentioned by the HP SDR guys, that's not usually the case. There's a lot of DSP actually happening on these devices. So this is a block diagram that I drew of my user P, my B210 to be exact. And what we see here is that it has an RX and a TX chain, and let's just talk about the RX chain for now. So we have this RX antenna, and it has an amplifier that I left out because kind of obvious we need that. Then we have a mixer, which mixes my 97 megahertz plus minus 12.5 megahertz. So we have this total 25 megahertz to 0 hertz. This only works because the output of that mixer is a I and Q signal, so it's complex. And so we don't have the symmetrical spectrum. We can have whatever spectral shape we want. It's not going to be symmetric in general. So after that, we have an A to D converter that actually has two channels that takes the I signal and converts it to a stream of samples and the Q signal. And they do that exactly at the same time. So we get actually pairs of real samples that we can interpret as complex numbers. So this is the start of our actual DSP chain here. So because, well, LO, the mixer needs an LO, and LOs need to be synthesized by something, and we want to synthesize arbitrary frequencies, but that's not going to happen in hardware without a lot of variation, a lot of temperature dependence and stuff. We use synthesizers that derive their frequency from a stable reference and can only do a discrete set of possible frequencies, some combinations of multiples and divisions of that base frequency. So we can't possibly reach every single frequency that we might want as center frequency here. And because that's not usually what one wants to tune to every frequency in exactness, we still have the possibility to tune in digital domain by basically multiplying with another mixing signal that we synthesize on the FPGA, and we can do that to a very high degree of precision. So now we have our 97.000 megahertz exactly at 0 hertz. And but that might happen at maybe 50 megasamples on other devices at maybe 200 megasamples per second, and we just wanted 25 megasamples because 200 megasamples pushing into a PC, no fun. Also totally unnecessary. We want 25 megasamples. We only need 25 megahertz. We have complex signals, so 25 megasamples is okay. So we decimate. So this is a decimator, and it basically, a decimator is like a ADC for signals that are already digital. So this sounds strange, but basically what it does is it only considers every second, or every fifth, or every 18th sample. Yeah? So it looks at the first sample, drops the second, looks at the third sample, drops the fourth, and so on. But what we're doing here is kind of the same as sampling an analog signal. And wait, we have to observe Nyquist Shannon theorem here, right? Because otherwise the frequencies in the other half of the spectrum that we ignore when we only look at every second sample will end up mirrored up on our spectrum that we want to observe. So what it does first is filter the signal, then drop every second or every fifth or whatever sample. So there's an adjustable filter in here, and with that filter comes the ability to drop samples, all but every nth. And then we just send things to the PC. Yeah, kind of where all the functionality is. I'm not going to go into detail here. But most of this is handwritten in the FPGA that we put on those boards, and quite some of that functionality is also often found in the front-end chips. So now that we have the signal in the PC, remember we are talking about 25 megahertz of bandwidth, and we want to have a FM station that is maybe less than 25 kilohertz wide in theory. So let's first decimate to 200 kilosamples per second. Okay, I'm going to speed up a little. So this is again, as I mentioned, exactly the same setup as on the USRP. We have the mixer, the digital mixer, and the digital low-pass filter, and the decimator. This is what's happening in the X-latent Fur filter here. That X-latent Fur filter is kind of interesting because it's a monster of a filter. Like no one would actually ever buy such a filter as an analog component because it's not going to exist, right? This filter has an attenuation of below 80 dB at 5 times its cutoff frequency, and the steepness. It's not practical to have such a filter in the analog domain. And it's still a total beast in the digital domain. 2045 taps means that I need to take every of my 25 million samples per second on the input, multiply it with 2045 coefficients, add the results up, and get one output sample. In theory, in practice, there are tricks to reduce the workload posed by that, so that even my constantly overheating 80-year-old laptop can do this in real time. So this is awesome. An analog filter that has nearly the characteristic would be more expensive than my laptop had been when I bought new. And this is totally overspecified. I mean, no one doing broadcast decoding needs to have such an SNR that this can ensure. This is FM broadcast. This is not transmitting something across the globe.
Maybe you can use a recursive filter like IR, but then responses and
So the comment is that for this I could use an IR, but in practice IRs on general purpose CPUs are worse than FIRs because, well, caches, basically. and SIMD instructions. So fmdmod pretty much does what the name says. The rational resampler is again a filter because in math it just interpolates by 50 and then decimates by 48 to match the mismatch that we have in here. I think I actually made a mistake. Whatever. In practice, again, we can switch that and first decimate and then interpolate by having polyphase filter. This is awesome because that's, again, a very, very nice filter that we actually have here, but it works at neglectable CPU usage. And the audio sync simply does what it says. It sends the samples to the audio sync, and we just get the raw audio. Well, to conclude very quickly here, we can represent any signal that we can observe in a digital form, as long as it's band limited and as long as I didn't put it there, but it's kind of obvious, the value of the signal cannot exceed what we can observe with our ADC. The question is how good we can do that, but I'm not going to go into that anymore. We have the constant problem of aliasing of multiple Nyquist zones into the Nyquist zone we want to observe. So we need anti-aliasing filters. But we can also abuse aliasing for greater good and use undersampling systems. In total, DSP is a really, really, really nice toolbox to build cheap systems that do awesome stuff that we could never do with analog systems. And so SCR really depends on having the ability to do great DSP in the end. And as seen by the whole of 5 blocks that make up a very selective FM receiver, toolboxes like GNU Radio make it really easy to actually do that as soon as you have the hardware that just gives you the samples. So that concludes my talk. Hope you enjoyed that. Well, if there are questions, don't hesitate.
Thank you, Markus. Are there any short comments? Very short. We are later on the timetable. Since a few minutes, Frank would talk.